In this video, we're going to discuss how to multiply matrices. So the basic idea is that matrix multiplication is composing linear maps. So we have one linear map that takes you from one vector space to another, and then we follow that up with a second linear map that comes from the codomain of the first map into another vector space. So here I have written down two linear transformations. S goes from R4 to R2, and T goes from R3 to R4. So what this means is that we can chain these together in the following way. So T starts in R3 and produces something in R4. So I'm going to label this with a T here. Okay. But S takes things in R4 and produces things in R2. So we can take a vector in R3, apply T to it to produce a vector in R4. And to that resulting vector, we could apply S to it and produce a vector in R2. So this means we get a composition map going from R3 to R4, which is S composed with T. Now at first glance, that might seem a little bit backwards. But remember, these are compositions of functions. And when we think about applying functions, we apply from right to left. So if we were going to take a vector and plug this in, first we plug it into T, and then we would take the result and plug it into S. So if we're talking about multiplying matrices, what we really want to do is, by definition, just write down the standard matrix for the composition map. So our composition map here is S composed with T. So the standard matrix for S composed with T is going to be the matrix AB by definition. So AB is the standard matrix of S composed with T. We put a nice box around this because that is the definition of multiplying these matrices. All right, so how do we actually do this? So the standard matrix, the columns are just given by what happens to our standard basis vectors. So all we have to do is figure out what the map S composed with T does to our standard basis vectors. So let's start with our first standard basis vector, E1. So we're going to take E1. First, we're going to plug it into T, and whatever we get out of there, we're going to plug into S. So the good news is that it's very easy to plug E1 into T. We just have to look at the first column of the standard matrix for T. And the standard matrix for T we call B. So all we have to do is write down the first column of B here. So 1, -1, 2, and 3. Okay. And now we're going to take that resulting vector, 1, -1, 2, 3, and plug it into S. So remember, what this means is we're doing a linear combination of the columns of the standard matrix for S, because this vector 1, -1, 2, 3 is a linear combination of our standard basis vectors. So that says we need to do 1 times the first column of the standard matrix of S, which we are calling A, so the first column of A, and then -1 times the second column, and +2 times the third column, which is 0, 4, and +3 times the last column, 2, -2. So now we just have to do a little bit of arithmetic here. So on the top, I think we get a 5, and then on the bottom, I believe we get a 4. Okay. So that's going to be the first column of our matrix AB. So maybe I'll change colors and write this over here. So AB first column is 5, 4. Okay. To get the second column, we need to apply our map as composed with t to our second standard basis vector. So remember, to figure out what t does to E2, we're just going to look at the second column of B up there, which is 0, 1, 4, 5. And to figure out what S does to 0, 1, 4, 5, well, that'll be 0 times the first column of A. So 0 times 2, 1, plus 1 times the second column, 3, negative 1, plus 4 times the third column of 0, 4, and plus 5 times that last column of 2, negative 2. All right, once again, we do a little bit of arithmetic, and we get 13, 5. So that is going to be our second column of the matrix A, B. All right. The domain of our composition map was R3, so we got one more basis vector to go, which means our matrix AB is going to have one more column. So first we'll take E3 and plug it into T. So we're looking at the third column of our matrix B now. Looks like we have 6, 7, 8, 9. So now this says we'll do 6 times the first column of A, which was 2, 1, plus 7 times the second column, which is 3, negative 1, plus 8 times the third column of 0, 4, and 9 times the last column of 2, negative 2. All right. And here we get 51 in the top spot and 13 in the second spot. So that is our third column of AB. So 51, 13. Yep. So that is how we multiply two matrices. So I want to note a couple things about this. So one, we can't always multiply two matrices. So one of the key things that had to happen was the codomain of our map T had to be the same as the domain of our map S. What that means for our matrices is that the number of columns of A, which is telling us the dimension of the domain of S, had to match up with the number of rows of B, which is telling us the codomain of T. So those both have to be the same. In this case, 4, telling us the codomain of T and the domain of S are both R4. The other thing I want to note is that as soon as we draw this picture up here, then we know what size our matrix AB is going to be. So the domain is R3, which tells us we're going to have 3 columns because we're going to have a column for every basis vector of our domain. And the codomain is going to be, well, the codomain is R2, but the number of rows is going to be 2, because remember, each column is an output vector of this. So each column better be an element of R2, so we are going to have exactly 2 rows.